So thanks for the introduction. I'm going to talk about ionic mechanisms for polarization switching in ferroelectric van der Waals crystals. And more precisely, I'd like to show you some work on copper indium thiophosphate, or as I'm going to call it from now on, short, CIPS. CIPS belongs to the family of transition metal thiophosphates. There's a variety of compounds with different interesting functional properties. And what kind of gives us a wide variety of functionality is just a layered structure. So we have those. It's not loud enough.
Apparently not, even for the controls. So let's try to do this here.
Here.
Yes, here. Try now.
Okay. Is it any better now? Okay, great. So we have this layered structure, the layers, we have van der Waals gap in between, and this kind of stacked structure allows us to exfoliate those crystals into kind of thin structures that are still electromechanically active and functional. On the other hand, cleaving leaves us with really nice, clean surfaces, no dangling bonds. They're just perfect to interface with 2D materials like MOS2 to create things like ferroelectric field effect transistors. So copper indium thiophosphate has some interesting ferroelectric properties on one hand, but also very nice ionic properties. And throughout this talk, I'd like to show you how we can utilize both of them, how we can access the ferroelectric regime, the ionic regime, and states in between to create some more functionality. When we're talking about accessing those ferroelectric and ionic regimes, how can we do that? Of course, the first thing that comes to mind is temperature, and I'd like to give you some background, kind of from the point of view of temperature. But we can also use electric fields to basically transition between ferroelectric and ionic properties or dominant properties. And from that point of view, I'd like to show you how we can use ferroelectric switching between 4 polarization states and ionic mechanisms for polarization switching. In the next step, we're going to talk a little bit about how we can activate and deactivate polarization switching using electric field just all together. The last part of my talk will be the role of relaxation time in activating, reactivating polarization switching. So copper indium diphosphate, it has been known basically since the 90s that it is ferroelectric. We have a polarization, a few microcoulomb per square centimeter. We have a transition temperature, a Curie temperature of kind of 310 Kelvin. That's just above room temperature, so not really high. What determines which polarization state we're in is where this copper ion is. Is it on top or bottom of the layer? On the other hand, we also have kind of high electrorestriction. So CIPS is somewhere here, right up there with polymers and glasses, whereas other ferroelectrics are orders of magnitude lower. So we do get, despite the low polarization, a kind of piezoelectric output comparable to PCT. So the important takeaway message from this slide is that ferroelectricity is associated with an ordered state, and in this case, copper mostly determines our polarization. And copper is kind of within that layer. So now if we increase temperature, copper becomes very conductive. Again, there's been some early work that determined that the most mobile ion in this compound is actually copper. So copper determines polarization, but copper is also the ion that just kind of flows through the crystals at certain temperatures under certain fields, creating a disordered state. We can take it even further than that. Copper can actually leave the crystal, forming crystallites on the surface at high enough temperatures, and then we can reinsert them again within the voltage cycle. So here we have a typical ionic signature. We have the temperature dependence, The higher the temperature, the more conductivity, but we also have copper conductivity at room temperature, but to a lesser extent, of course. And we have a frequency dependence, so the slower, the more conductivity. And that's going to be important in a couple of slides. So now what happens if we just have the temperature fixed at a constant value, which is in our case just room temperature, because that's where we do most of our measurements. We can use the electric field for ferroelectric switching between 4 polarization states, and I'd like to give you some more information on that. Why 4 polarization states? So it turns out that this part that I just showed in the ferroelectric background is only half of the story. Density functional theory has shown that in addition to those polarization states here, copper can also slightly displace into the van der Waals gap and form a second phase. This is possible because instead of the usual double well, ferroelectric double well, here we have actually a quadruple well. We have the so-called low polarization phase here with kind of 5 microcoulomb per square centimeter corresponding to those panels up here. The bottom panels, they correspond to the high polarization state, or HB state, where we have something like around 11 microcoulomb per square centimeter. This quadruple well is highly dependent on strain. If we apply tensile strain and we have a lattice parameter of 13.6 instead of 13.09, we get very pronounced minima in the low polarization state. If we squeeze the crystal, apply a compressive strain, we get just the opposite situation. We mainly end up in the HB state. This is because by compressing the crystal, we mainly compress the van der Waals gap, making it easier to form bonds across the layer as it's done for the high polarization phase. So we also have some values in between, and altogether the quadruple well is very tunable, dependent on strain. So now that we know we can actually have 4 polarization states in this crystal, we want to, of course, experimentally verify and identify polarization states. We can do that because density functional theory also gives us the stress dependence of polarization. And from the gradient, we can extract piezoelectric coefficients in our directions of interest. And it turns out for the low polarization phase, we get something around 16 picometer per volt, and the slope is negative, indicating negative electrostriction. Whereas for the high polarization phase, now we basically end up with a 3D crystal. We get less stress dependence, translating into a smaller piezoelectric coefficient, and it is positive. So that's very different, and we should be able to see that in piezo response force microscopy. And we actually do. This is an example of a PFM scan where we map out the effective piezoelectric coefficient in vertical direction. We have here those kind of rivers. They are zips, and it is all embedded in a copper-free different chemical phase that is not piezoelectric, which is kind of nice because you can use it a little bit for calibration and rule out kind of electrostatic artifacts and things like that. If we plot the histograms, we can see that the maxima here very nicely corresponds to the theoretically predicted piezoelectric coefficients. So we use that basically to identify our polarization states. We can in principle do it pixel per pixel and track down kind of how domains evolve over temperature. We can also apply a different strain, or as we actually do experimentally, we use our PFM tip and we just press harder and harder and see some interconversions, for example, between here where it's all blue, so that this would be the plus HB phase to the minus HB phase where it's yellow. But most importantly, for applications, we can also transition between polarization states. So let's have a look at those 3 hysteresis loops. So by the way, they occur in different parts of the sample, and basically clusters of pixels show that type of behavior. For the green curve, that's kind of the standard hysteresis loop. We have polarization switching from positive to negative if we apply positive voltage. But we can also have those blue and red curves where, in addition to polarization switching, we also have phase transitions between the high polarization and low polarization phase. But all in all, it is still ferroelectric switching, meaning polarization aligns with the electric field. In the next couple of slides, I'd like to show you how we can use an ionic mechanism to get a little bit more peculiar behavior. So we talked about how ionics is kind of slow and field activated and frequency dependent. So in this setup, we used longer voltage pulses. We have the -6 voltage pulses from 100 milliseconds to 1 second, and reset pulses of 2 seconds. In this particular case, we used like a atomic force microscopy setup, and we could image piezo response through a nickel electrode in a capacitor structure. After each of those pulses, we looked at the piezo response force microscopy maps and kind of had a look, how did our polarization states, how did they evolve? This is done without applying a DC field, so we see kind of the relaxed state. Okay, here it is. As a quick reminder, again, these are the 4 polarization states that we're able to see, or maybe able to see. We start out with everything being mainly in a negative low polarization state. Then we apply longer pulses. We start getting some nucleation. We starting to get some domain growth. And then as we progress in time pulse duration, we suddenly end up in a positive low polarization state. Do you still not hear me? Okay. Okay, so we start out mainly yellow, and then we start out mainly blue. And we see some spatial correlation, but we also wanted to see how can we actually get some statistics on transitions between those polarization states. So I basically analyzed all those pixels, had a look in what states are they first and before a pulse, and what state are they after a pulse, and then created a Sankey diagram. And it didn't absolutely clarify things, but basically what we can say is at first we are mainly yellow, meaning negative low polarization. After 1 second, we're mainly positive low polarization. And there is a lot of complex switching paths in between. And that's why I would like to walk you through one path in particular, which is this one. So we start out in a negative low polarization state, -5 microcoulomb per square centimeter. And then from half a second, we switch to a positive polarization state, just in the direction of the electric field. We end up with a higher polarization, then suddenly switch to a negative polarization, and then to a positive polarization again, which is kind of very peculiar. But it makes a little bit more sense if we think about the path of our copper, our positive copper ions, and if we think about the kind of crystal structure during all of those steps. So we start out with this minus low polarization phase. We have our copper here in the schematic. We switch to the top of the layer, end up with a high polarization state as the copper goes further towards the top electrode where we apply the negative voltage. And then it happens. So then we get this kind of peculiar peak here, where copper moves across the gap and creates a negative polarization, even though we apply a field in the opposite direction. And in the end, we kind of go to the positive low polarization state again that we already passed here. So this is only possible if we can drag copper across the van der Waals gap. And we actually know that we can. We know it from density functional theory and experimentally that we have activation energies that are actually not that high. We can see currents. Then the kind of the idea of dragging ions across, like beyond unit cells, is dependent on the electric field. Is not even that new. Scott had a paper on silver salt where he wrote something along the lines: if you apply negative voltages, the ion is within the double well and switches back and forth. And if you apply higher voltages, the copper basically, not the copper, the silver just goes through the crystal. So as a consequence of moving copper across the van der Waals gap, we have an ionic switching mechanism that is very different from the ferroelectric dipole alignment. And then that allows us to do something that a pure ferroelectric would never allow, which is we can switch the polarization against the electric field, which also means that we can apply a unipolar voltage pulse and kind of cycle through positive and negative polarization states. So what else can we do with electric field activated ionics? The answer is we can just activate and deactivate polarization switching altogether in this crystal. Here we did some PE loops at Purdue University in a more, it's still not really macroscopic setup, but we have those 20 times 20 micrometer electrodes, we have micromanipulators, and we acquire PE loops by applying this triangular voltage pulse, measuring current peaks, integrating, and getting our PE loops. We start out with a really nice ferroelectric hysteresis loop. In the next step, we apply minus 10 volts for 3 seconds, just a square pulse through the electrode. And if afterwards we want to measure the PE loop again, we just get nothing less. There's absolutely no switching in this state. If we then apply a positive voltage pulse, so this one was negative, now positive, we suddenly kind of reactivate ferroelectric switching and end up in a nice ferroelectric polarization switching state again with loops that are they actually look even nicer than before. So that's kind of nice that we can just apply long voltage pulses and then decide whether we can basically now decide, do we want a positive polarization state, do we want a negative polarization state, or no switching at all. So we can switch between hysteretic and non-hysteretic behavior on top of polarization switching. Now let me show you what relaxation time basically does to the system. Again, this kind of a similar experiment. This is the piezo response force microscopy set up again. Now we have our microscopic probe on our small capacitor. We have a triangular waveform to kind of acquire similar kind of switching loops like in the previous slide. These are now current versus voltage graphs. And in the beginning, we have those kind of peaks, a little bit of onset of conductivity already, but it clearly indicates that there is some ferroelectric switching with some polarization reorientation. If we apply negative voltage for 1 second, just a square pulse, suddenly we end up with no current peaks. Then I thought, keeping the previous slide in mind, okay, I can just apply a positive voltage pulse and bring back switching, but in This was not the case for this experiment. It was a different capacitor. It is the probe is much smaller, and the crystal was much thinner. It's just like tens of nanometers. So I let the system sit for a while, and then did the same experiment again. And suddenly, just all by itself, switching was back, and I saw nice switching peaks. So this kind of tells us that time is important. And it also tells us that even though ionic conductivity and ferroelectrics or a dipolar ordering might be sometimes be seen as incompatible, it can be that we can access ionic conductivity, lose all the polarization switching, but that the system gravitates towards a polar ordering again if you give it enough time. And that's kind of interesting. So we have this additional parameter, relaxation time, in addition to temperature and electric field. So to summarize this, in conclusion, copper indium diphosphate is a ferroelectric. It has a tunable quadruple well, so we can have polarization switching aligned with the electric field, sometimes purely polarization switching, sometimes in combination with phase transition, high polarization versus low polarization. On the other end of the spectrum, we can have ionic properties. So we have a very high copper conductivity, temperature dependence. We can even reversibly extract copper from the crystal at higher temperatures. But what's the regime that's actually really interesting is the regime kind of in between the purely ferroelectric behavior and the purely ionic behavior, where we can move copper across the gap, which just allows us to switch the ferroelectric polarization against the electric field, or even activate polarization switching altogether and then reactivate it again. And we can do that using temperature, electric field, and relaxation time. So as an outlook, I showed you basically those three parameters that we can have, but the reality is those are expected to be very interdependent. So it would be good to map out kind of at what fields and at what temperature and what relaxation times can we reliably access those transitions and intermittent regimes between ferroelectric and ionic polarization switching. Also, in the next step, there's some other control parameters that could have an impact, for example, strain, then even the field history, sample geometry, and internal and external interfaces. But for now, I'd like to thank you for your attention, and I'd also like to thank all the collaborators at Purdue University, at the Air Force Research Laboratory, and Vanderbilt.
Time for questions.
This, the kind of activation and deactivation of the hysteresis loop, is that, can you do that over multiple cycles?
Yes, so I don't know yet if I can do this like 100 times, but it worked a few times. What's a little bit of a problem is that sometimes voltage history matters. So once we've done a lot of experiments and applied a lot of very long voltage pulses, then it's not possible anymore to bring back. But it works, like it was not that this worked one time and now I'm showing it. So.
Hi, I think it's a very interesting system. I'd like to offer a different possible interpretation. Rather than saying that the polarization switches backwards, I wonder if this is a case where it really switches forward onto the next value of the polarization lattice. In other words, it looks to me like this may be a case of what's called quantum adiabatic charge transport. That is, when you go around the cycle, you've really actually moved a copper 2+ ion up one layer, and it's carried charge with it, and it's basically carried you from one from one value of the polarization lattice to the next at the end of the day. So I don't know, maybe this is to discuss offline. I don't know if you've tried to think about it in these terms.
So, but you mean basically this jump?
Exactly, that jump.
Yes, yeah. So that's basically what we're saying. So that this copper ion can switch to the next.
Yeah, I guess another way of putting it is in the context of some of the earlier talks, if one would do a DFT calculation where one follows that copper ion in small steps, you'd find actually that the polarization kept going up.
Okay. Like, thank you. I mean, yes. I'm gonna think about it. That, what we measure is, what we experimentally measure is that the polarization is flipped.
So you measure
piezo, right?
Yes, yeah.
That's the difference.
you measure
You have four inequivalent sides, which has each four inequivalent signature in piezo. And therefore you know at which of your steps are modulo 4. And you call that polarization state, but it's equally valid what David is saying, that of thinking that polarization is I mean, if you would measure the charge which goes across, then your hysteresis loop probably would have 4 steps, right?
Yeah.
And just as a comment, so if we were to repeat the calculation across the gap, there would be a paraelectric state right in the, well, okay, so not paraelectric, P0 state right in the middle of the gap. So it goes through 2 centrosymmetric structures, one in the middle of the layer, the other one in the middle of the gap. And so in the state that's, let's see, plus HP, that's close to the largest polarization, and then it drops toward the middle of the gap and then picks up on the other angle. But the quantum of, so this is, it kind of wraps around. So would be happy to discuss how, but that actually makes sense, so to speak. But, and you're right that the piezoelectricity is concealing to a certain degree the details of what's going on, but yeah, still identifiable states are possible due to the difference in the tensor.
So it's a polarization like this with a structure inside. It's not simple.
Yeah, following on this, to add a bit more of yet another possibility, I truly cannot see, I mean, from a step 1 to a step 2 there, or from a step 4 to a step 5, I think you are crossing the layer.
Yes, here we cross the layer.
I mean, not the Van der Waals gap. You actually, your copper crosses the layer, right?
But from here to here, we cross the layer.
No. From number 4 to number 5, for example.
Yeah, from 4 to 5, this is just normal ferroelectric switching.
But the copper crosses the layer. I mean, so your copper atoms actually are a current, eventually, that crosses both the Van der Waals gaps and the layers themselves.
Yeah.
So it's really, it's exploring the whole lattice.
Yeah, so basically copper consistently goes up, and as it goes up, basically polarization changes.
We have time.
Just how thick was the sample?
We've measured different samples. So in this particular sample, it was 117 nanometer thick, and the electrode is 20 nanometer thick. But we see similar behavior in micrometer thick crystals too.
Okay, so if there are no more questions, let's thank our speaker again.